So we have one more idea we're going to talk about in section 3.2. Actually, I guess two more ideas. And so far, this is the data from the previous lecture. So this is there's some melons. The first column is the diameter of those melons in inches. Second column is the weight of those melons in ounces. And so I've made a scatter plot. On the x-axis is diameter, y-axis is weight. And I've drawn the equation of the LSRL. Okay, or I've drawn the LSRL, which is the line of best fit. The next idea we're going to talk about in relation to this data is something called a residual. And a residual is the distance each point is from the line. So each point, each melon, has a residual. So you'll see how for this first point it's a little bit below the line. So that point has a negative residual. Whereas this point, the second point, is above the line. It has a positive residual. This one has a residual that's almost zero, but actually if it was zero it would be on the line. So maybe a little bit negative. And this one has a big positive residual, and this one has a negative residual. So like for example, for this last point, how would I calculate how big the residual is? Well, where this point actually is right here, that's 8.9, right? That's the number that is the actual y value. This number right here is what you would predict the y value to be. And then we subtract those. So the formula for the residual for any point is the residual is equal to the actual y, which is the number that would be in the actual data, minus the predicted y. And usually you would find the predicted y by figuring out the equation of the LSRL like we did last lecture and then plugging in the value. So we see how each point actually has a residual. And you could calculate those residuals for each point, right? For any melon, if I said for this melon, calculate the residual, you would do 7.1 minus what you would predict the melon to be with a diameter of 3.9. Let me just kind of quickly draw another scatter plot. We're going to just kind of make up some numbers here. So this is for a bunch of people. I don't know, it's like their weights and their heights. So I don't know, maybe it looks like this. Let's just kind of a few people here. Boom, boom, put a point there. Okay, good. So the LSRL through these, if I were to do a line of best fit, I don't know, maybe something like this. Okay? And there's actually a graph you can make for these points called a residual plot. It's another kind of graph. And the way you make a residual plot is you plot, instead of plotting, you plot weight on the x-axis still, but instead of on the y-axis doing height, you plot the residuals. That's why I've put 0 in the middle, because actually the point on the line is 0. So you see how this point has a negative residual, the first point? So we'll put a dot right there. And then this point has a positive residual that's above the line. We have two negative residuals. One looks like a little bit bigger than the other. Then we have kind of a positive residual up here, it kind of looks like. Then we have a point on the line, which has a residual of 0, and a point right there. So this green thing would be a residual plot, and your calculator can make residual plots for you. Okay? We'll talk about that a little bit kind of later on. But x-axis is the same as it was before. Y-axis is residual. Okay, now why do we care about residual plots at all? Let me just make up a couple more scatter plots. So the scatter plot in orange this time is going to be, I don't know, some relationship. Maybe it's like a ball or something. And actually I'm going to draw a scatter plot that is very clearly non-linear. So this is an association that is clearly not linear. And now if you were to make a line of best fit through this, for the LSRL, can't really do a good job making a line, so it's going to look something like this. Perhaps, maybe a little higher. So I want you to think, what would a residual plot look like for this? Well, you would draw this. And one of the things you might notice is that these points all have a negative residual, these points all have a positive residual, and these points all have a negative residual. So what would the residual plot then look like? You have a couple points below the line, a whole bunch of points above the line with kind of this pattern, and then a bunch of points below the line. See, this actually has a pattern to it, the residual plot does. This actually leads to an important idea, which is if the residual plot, which is this guy, this is the residual plot, if it has a pattern, then the original scatter plot or the original association is nonlinear. Let me say that again. If the residual plot, which is this, has a pattern, then the association is nonlinear. It's an important idea. Let's write that down. If the residual plot has a pattern, then the association, abbreviating, is nonlinear. Now in the previous example, you're probably thinking, well, duh, I mean, that association was so nonlinear, it was so obvious. But you will get scatter plots from time to time that kind of look something like this. And you might think, well, gee, that's a pretty darn good, kind of looks like a straight line, sort of. But notice there's a little curve to it. So a LSRL through that might look something like this. And now I'll kind of do what I did before, which, look, these points are all above the line, they have a positive residual. These points are all below the line, they have a negative residual, and these are all above the line. So here, even though it's a little bit more subtle, the residual plot might look something like above, 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 below, 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 above, 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 and then there's your pattern, kind of more exaggerated on a kind of a different scale. Now let's compare that to some other random association or some other data. Hold on, let me do a different color here. There we go. Okay, isn't that fun? See that disappear? Magic. Okay, so here's a scatter plot. I'm just going to do a bunch of points. Da, 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 da. Look how fun this is. And the association is not very strong, but it kind of does look linear. There's certainly no curve to it. And if you were to draw an LSRL through these, the line of best fit, I don't know, maybe something like that, and then a residual plot of these, you might say, well, look, there's no real pattern. You're just going to have some points above the line, below the line, above the line, kind of and so on, right? Here, you notice there is no pattern in the residual plot. Here's the residual plot. There's no pattern. And that tells us the original association is linear. No pattern in the residual plot. The original association is linear. Okay, let's write that down. If there is no pattern in the residual plot, then the association is linear. And we're writing those two ideas down because it's confusing, because it's like if there's no pattern, it is linear. And the previous sentence was vice versa. A little bit tricky. Okay, the last idea I want to go back to what we kind of did the previous, with my Mellon data. Remember we talked about the idea of R. Okay? And R was called the correlation coefficient. Correlation coefficient, which you may remember from a previous lecture for this Mellon data, R was 0.7879. When we found that on the calculator in class, you may remember that actually it also gave us R squared. And R squared actually has a name. It's called the coefficient of determination. Determination. Oh no, it's not going to fit. Determination. Not bad. And so it turns out for this particular Mellon data, R squared was 0.6208. And the coefficient of determination, or R squared, actually is a little bit more important than just finding it and square rooting R. Okay? And it turns out that the R squared, the coefficient of determination, has a magic sentence that kind of is associated with it that kind of tells you what it means. And R squared is the percent of variation in Y that can be explained by variation in X. So for this particular Mellon data, we might say 62.08% of the variation in, and what was Y now? Y was weight of melons can be explained by variation in, and then what was x? X was diameter. So there are some people that just kind of get through AP Stat just kind of memorizing that phrase, the percent of variation in blah that can be explained by the variation in blah. On the next slide, I want to kind of give you some understanding of what that means, but if you don't quite get this understanding and you just memorize this phrase, you'll actually be okay. Okay? So what I want to do is kind of just think about, like, imagine you've got some big bamboo plant, okay, planted in the backyard. And obviously, different bamboos grow at different heights. Different bamboos grow all over the world. Okay, let's kind of think about that in terms of like a pie chart. Okay? So would you agree that there is some variation in bamboo height? Clearly not all pieces of bamboo are the same, right? So what are some of the factors that control the variation in bamboo height if we were to kind of make it like a pie chart? I'm not a biologist, I don't really know, but let's kind of just say, well, one thing you might think, okay, well, is water, right? Probably the more you water things, right, the taller it's going to be. If you water bamboo plants at different rates, some will be taller, some will be shorter. Sunlight might kind of be an important one, right? The type of soil, right, might be super duper important. Okay, there might be some other things, like fertilizer, right, might be something kind of important, I don't know. Made that smaller because it seems like soil is probably more important than that, right? Maybe there's some other things, like there's like the type of seeds it is, okay? Or maybe, I don't know, the last thing is bugs could be a little factor. Or, I don't know, maybe like as you sing to your plants, I don't know, I'm making this up, but, you know, singing to your plants might actually make them grow taller or shorter. Well, notice, let's kind of say that, like in the case of this sunlight, I tried to make it so it's about 25% of the whole thing. This kind of gives you an intuitive notion of the sense of what the sentence I wrote on the previous page, where you might say here 25% of the variation in height can be explained by the variation in sun. So if you could somehow make a scatter plot here and do a plot, 25% of the variation in y can be explained by the variation in x, whereas the other 75% of the variation is explained by other factors we can control. So think about that sentence I wrote on the previous page now. 62% of the variation in, okay, let me write it again. 62% of the variation in melon weights can be explained by the variation in diameter. So if you imagine, you know, what are the different factors, just like I said here, there's different factors that control the height of bamboo. Aren't there a bunch? Hey, where was I? So 60% of the variation in melon weights can be controlled by the variation in diameter. Lots of different factors control or influence how heavy a melon is. One of them is diameter, but there could be others, like the type of melon, water, all sorts of other things. But we're saying that if you were to make a pie chart of this, 62% of it, so which is a pretty big chunk, would be melon weights. Okay, and that's it.